Good afternoon, everyone. I see only one participant so far. Excuse me. Okay, let me just see. To the student who's currently tuned in, can you hear me?
Yes, sir, yes, sir.
Okay, cool. Okay, now today we're going to be doing some problems on. Let me just make sure everything is live. It's streaming. Okay, to the questions, we'll be doing some problems on sound waves and superposition of standing waves. Okay, so let's start. Okay, question 14. If you want to review the first 13, Arnold has already done them last week. So I'm just continuing on. Okay, so question 14. This is a relatively simple problem. It just asks, and it says, state starting. Do not try the following, it could kill you. Okay, this question is only about a hypothetical possibility. So the question is, if you were standing below an object emitting a fixed frequency sound falling at terminal velocity, okay, that means it's not accelerating anymore, it's falling at a terminal velocity. As it approached you, you would hear the sound. What would you hear? A drop in the frequency? Would the frequency stay the same? Would the frequency increase? Would the frequency decrease in loudness or stay at the same in loudness? Okay, now the loudness will not be affected, so it'll be frequency. Now it can't be a drop in the frequency because, well, number one, it is coming closer now. So the question then is it B or C? Will the frequency stay the same or will it increase? Okay, considering that we've done other problems where frequency increases when something gets closer, one might be tempted to think that it would be C, the increase in the frequency. But in actual fact, let's look at B. Okay, the frequency in this case would stay exactly the same if something is falling from terminal velocity. The frequency will not change. Okay, so the frequency will not change. The answer for number 14 then is just B. That is just something to think about. The frequency will not change as something is approaching you at terminal velocity. Now, if we were to move on to question 15, which is actually where the questions technically start, because this is the calculation part. Now, if a plane is flying at a speed so that the apex half angle of its shock wave, okay, when something is flying at supersonic speeds, it creates a conical angle, this angle here, a
Yeah.
cone. Okay, so when it flies, it creates a cone. Okay, now the apex half angle is this angle, the angle that the cone makes with the line running through the center of this cone. Okay, so they are asking us, if a plane is flying at a speed so that its apex half angle of its shock wave is 30 degrees, meaning this value here is 30 degrees, what is its speed in the speed of sound if the speed of sound is 320 meters per second? Okay, so what is this thing's speed? We know that the formula for a Mach number is equal to the sine of that angle is equal to, or rather, let's write it this way. Yes, 1 over m. Let me just see if everything is fitting on there. The sine of that angle is 1 over m, where m is the Mach number. Okay, that's how you get those values of Mach 1, Mach 2, Mach 3. It is just a multiple of the speed of sound. Okay, instead of saying it is traveling at 320 or double 320, we just say Mach 2. Okay, it is just a multiple. That number just indicates a multiple of the speed of sound. Now this angle is the sine of 30 degrees, and that is equal to 1 over m. Now you calculate m. If you were to determine m, you would find that m 1 over the sine of 30 is equal to m. Now if you are well versed in your special triangles, you'll know that 1 over the sine of 30 is equal to a half. Therefore, if you were to write it out, 1 over sine 30 is equal to 2. So m is equal to 2. Okay, now what can I do with this value of m equal to 2? Okay, now m equals to 2 just says that this thing is traveling at twice the speed of sound. Okay, it's traveling at twice the speed of sound. Okay, so m, this Mach number, is equal to the speed at which this object is traveling. It can be a bullet, a jet aeroplane, and you divide it by the speed of sound, and that will give you your Mach number. Okay, that is how you get this value of a Mach number. Okay, it is just a multiple of the speed of sound, where Vs is the speed of sound. So we've already determined that we want V, right? We want the speed at which it's traveling. We know that the speed of sound is 320 for this instance. And we have determined that the Mach number is 2. Okay. Therefore, if you work it out, V is equal to 320 times 2, which is 640 meters per second. Okay. And you could have just guessed that the minute you calculated m, you knew that just m multiplied by the speed of sound should give you the speed of this object. Okay, because a Mach number, something's Mach number, is just how many multiples of the speed of sound is it traveling at. Okay, does that make sense? Whoever's still listening, does that seem reasonable an assumption to make?
Yes, sir. Yes, sir.
Okay, so a Mach number is just the number that indicates how many multiples of the speed of sound it is. Okay, so question number 16. They tell us, question 16, it is possible to hear an approaching train before you can see it. Okay, by listening to the sound wave through the track. Okay, now if you should have done wave motion B now, and you know that sound travels much faster in most cases in a solid. So if the elastic modulus is 2 times 10 to the 11 newtons per square meter, that's just some pressure, which we call a specific value of the elastic modulus. And the density of the steel is 7,8 times 10 to the 3 kilograms per meters cubed. Approximately how many times faster is the speed of sound in the track than in air if the speed of sound in air is 340 meters per second? Now, first of all, let's determine what is the speed of sound in this track. Now we know the speed of sound in a solid is equal to the square root of the elastic modulus divided by the density. If you have not seen this formula, you should have seen it in Survey and Jewett. If you have not done it, then this is just a fun way or something new to your arsenal of knowledge. But if you're a VV student, you know we don't go into depth for elastic or bulk modulus, but these are question bank problems, and I can show you how to determine them. This formula you should have seen at least. It's the elastic modulus divided by the density, and if you were to find the square root of that, you'd get the speed of sound in that material. Okay, so the elastic modulus is given as 2,0 times 10 to the 11 newtons per meter square, and 1 newton per meter square is just a Pascal. And then the density of steel is 7,8 times 10 to the 3. If you were to work this out now, I used to put up a calculator. It just takes some time to do, but you can plug this in your calculator on yourself. But you will find that the answer is indeed, or is 5,063,7 meters per second. Please note that I used only SI units. Okay, the density is in kilogram per meters cubed. The answer would be in meters. That would be kilogram newtons divided by kilograms, and your answer will be left in meters per second. So we have that the speed of sound in this case is 5,063,7 meters per second. But they asked us how many multiples of the speed of sound is it. Okay, so for that ratio, you need the speed of steel, and you divide it by the speed of sound in air. The speed of sound in steel divided by the speed of sound in air. For steel, it's 5063.7. And for the speed of sound in air, it's 340. And this will give you how much faster it is. And it's approximately, or it should be 14.9 times faster in, and that's a lot. It's 14.9 times faster in steel than it is in air. Okay, let's check. 14.9 is approximately 15. They rounded up. Let's check if 15 is correct. Okay, it is correct. Okay, it is correct. Okay, so next question. Let me just check something. Here we have question 17. Let's see what this question expects of us. Okay, question 17. They say the fundamental frequency of above middle C on a piano is 440 hertz. Okay, this is the tenor high A. Okay, now you don't need to know a lot of music knowledge for this question, but you do need to know about fundamental frequencies and harmonics. Okay, now this is the tenor high A. Okay, but a convenient note in the mid range of women's voices. Okay? When we calculate the wavelength, we find that it is okay. So first, let's calculate the wavelength of this wave. Okay, this frequency of the note. Okay, the frequency of the note is given as 440 hertz. Okay, now how do we calculate wavelength from frequency? We know that wavelength is just speed divided by frequency. Okay, so let's calculate the wavelength. Okay, it is 343 meters per second that I usually take as the speed of sound in the book. And then 440 hertz is the frequency. As the frequency. Now, if you were to calculate that out, you would divide 343 divided by 440. You would get some wavelength in terms of meters, because this is per second as well. Seconds would cancel out and your units would be in meters. And if you work it out, you get approximately 0.78 meters. Okay, 0.78 meters. That is 78 centimeters. Okay, now the question is, when we calculate the wavelength, we find that this wavelength is it much shorter than the length of either a man or a woman's lips? No, unless someone's lips is a 78 or bigger than 78 centimeters. This is longer, shorter than the length of a man's lips, but about the length of a woman's lips. No, that cannot be it. In this case, 78 centimeters is the longest, is longer than a pair of lips, whether it be a man or a woman's. Okay, 78 centimeters is twice the length of two rulers, and plus 18 centimeters added. It's almost three rulers length. Okay, so it's much longer than the length of either a man or a woman's lips. That one, number D, it's much longer than a man or a woman's lips, because this is 78 centimeters. So that wavelength is longer than a man or a woman's lips. Let's choose answer number D. And yes, it is correct. You see the small correction mark there. It is much longer than a man or a woman's lips. Okay. I don't know what the record is for the longest pair of lips, but I doubt it's even close. Okay. So 18. Okay, question 18. Okay. If you don't understand anything, just let me just check. Ask me a question or type. I saw someone just type something. Or okay, someone said they can't see the questions clearly. Let me just see if I can make an adjustment. Okay. Uh, yeah, here we go. Okay. Increase the question size. Okay, here we go. The questions are much bigger now. I hope you can see them clearer now. We are question 18. It has to do with the variation in pressure. The student who asked or couldn't see the questions clearly, I hope it's better now. Let me just see who asked the question. Azola, is it better now? Remember, I'm also sharing my screen to YouTube, so I include both the questions and the workout example. Okay, Zola, if you're still typing, I'm just going to wait for a minute. You still can't see them clearly on Teams. Wait, let me see. No, you don't need to go to YouTube if you're already on Teams. Just stay there. And I see. And YouTube, it's decent. You can. You can't see them exactly clear as well. It's because they have to be squashed in because I can't take the whole screen. I need to show the workout problems, okay? So, I don't know. Let me see. Okay, I think I'll do this. Okay. Just listen to the question rather than if you a PHYV or a FVV student. If you're PHYV, you should have access to all of these questions. Okay. PHYV students have access to all of these questions. I need to move some of them also to FVV. But anyway, I'm going to continue reading. Let me see. You can see them more or less clear, somewhat clearer on YouTube. Yeah, you can see them better on YouTube. Okay. So if you're rewatching it's much clearer on YouTube. But for those of you who are just tuning in now, can you just, Azola, can you just, rather than listen to the question, I can't see. It is TUT number 9, Azola. This is tutorial number 9. It's question 14. Okay. So, also, can I ask you something? Okay. Thanks for giving that heads up. If it's not clear on Teams, because originally this system is designed for YouTube only, so you can rewatch how we do the questions, but it is exceptionally clear on YouTube. But if you really want to know what the question, just listen to what I'm asking. In this case, the question is, let me just see that everything is still set up. Yes. 19, yes. Okay, so we have this question, okay, on pressure variation. It says the variation in the pressure of helium gas measured from its equilibrium value is given by, so the variation in the pressure delta P is equal to 2,9. I'm going to write down everything that's been given, times 10 to the negative 5. I assume that's pascals. That's the variation in the pressure. Is given by that formula. And then we have okay, let me just say, seems to be one complete formula. Is this question 19? Oh, yes. It's delta P is equal to cosine delta P max. That's delta P 2,9. I just want to check 6.2 and 3000. Yes, I did have the right one here. Okay, so the formula is, there is something missing there. Delta P is equal to 2,9 something. Cosine 6,20x minus 3000 t that's this is equal to this. Okay, that is equal to that 2,9, and it's not 29, sorry, it's 2,9 times 10 to the negative 5, or rather, sorry, my mistake, 19. This is delta P max. Okay, yes. So the formula, they give us this function as the change in pressure is defined by the function 2,9, where 2,9 is delta P max. Cosine 6.2 x minus 3000 t, and that's the formula. Okay, that is delta P max. Okay, now they ask us determine the frequency in hertz of the wave. How do we get angular frequency? We know that angular frequency is 2 pi times the normal frequency. Okay, now we want this one, the normal frequency. So the frequency is equal to the angular frequency divided by 2 pi. Where is the angular frequency? It's 3000. Okay, the angular frequency is 3000. So we divide 3000 by 2 pi. That is equal to, if I worked it out correctly, should be around 477.46 hertz. That's the frequency, the linear frequency. Okay, that's the linear frequency. And if we were to check on our, which one this is, let's check the linear frequency, or rather check our options. That's 4077. If we round it down, 4077, let's check. Bingo, it is the correct one indeed. Okay, so this is the formula for the maximum pressure, or the pressure amplitude. Okay, the variation in pressure. Okay, was that 18? That was number 18. Yes, this was not 19, it was 18. This is why I'm confused, because I wrote 19 in down, but the question is for 18. Okay, now we actually do 19. My apologies. Now we actually do 19. And question 19 says the velocity of sound in seawater. Okay, so the velocity of sound in seawater. So we write the velocity of sound in seawater is equal to 1,5 3 times 10 to the 3 meters per second. Okay, find the bulk modulus in newtons per meter, that is just basically Pascal, of seawater if its density is, then they give us the density, it is equal to 1,03 times 10 to the 3 kilograms per cubic meters. Okay, so we have the speed of seawater and we have the density. Now there is a formula which relates the speed in another medium, okay, in other mediums besides air. So it is the velocity is equal to the bulk modulus is equal to the square root of the bulk modulus divided by the density. It is similar to the one we did earlier on for solids, which is the elastic modulus we had there, but in this case it's just the bulk modulus. Okay, so we have the speed. It is 1.53 times 10 to the 3, so it's 1530 meters per second in seawater, and then the square root of the bulk modulus, which is what we want to calculate, and we have the density 1030 kilograms per cubic meter. Okay, so this is what we have so far. Now if you square both sides and then multiply by 10,000 or 1030 rather, therefore the bulk modulus is equal to the velocity, which in this case is 1.5 1.530. You don't have to write the 0. 10 to the 3 squared multiplied by the density 1030 kilograms per meters cubed. This is meters per second. You will get an answer in pascals. Okay, if you work it out, you find that your answer is 2.411 times 10 to the 9 newtons per meter squared, or 2.411 mega newtons per meter. So let's check. Okay, someone has your hand raised. Just ask away. Okay, I see a hand raised. You can ask.
So say,
Okay, you go ahead.
I have a question here.
Okay.
You were given the density of
Yes.
this scenario.
Yes.
Why are we using the density given here if the bulk modulus is in water? I want suppose like I want to know like I get the density of water independently. Then there's this density. Like how would I know that I'm supposed to use the given density, not the density of water?
This is the density of seawater.
Oh,
Remember, this is in seawater. So we are determining the bulk modulus of seawater.
okay. I thought it's a different density.
Or for seawater and water, they have different densities, yes.
You, I, I, I didn't know that.
Pure water has a density of 1,000 kilograms per cubic meter.
Yes.
Seawater has a density of 1,030 kilograms. It's a bit denser. And then you also have like pool water has a density of 10,020 kilograms per meter. They all have varying, because you see seawater has salt in it, so it should be much denser. Right.
Okay, I understand.
Okay, cool. So we determined the bulk modulus to be 2,4 times 10 to the 9 meters, or newtons per meter squared. Let me just see. Yes. Now let's check here. Which one is closest to 2,4? Okay, here is a 2,41 right here. Option D. Let's check if it is indeed option D. Does that, oh, rep, there we go. There's that green correction mark there. So this is indeed correct. Let's go to question number 20. Okay, I don't like to keep students long because I know you guys have a lot of other things to do. So let's go to 20. The question is to decrease the intensity of the sound you are hearing from your speaker system by a factor of 36. You can. Okay, now this is an interesting question. Okay, and it all has to do with the ratios. Okay, you want to decrease the intensity of the sound from your speaker by a factor of 36, so you want to make it 36 times less, the intensity 36 times uh uh less than it is now. Okay, so which one would you do here? Reduce the amplitude, reduce the amplitude by a factor of 4. Okay, so this is how you go about solving this problem. Okay, it is quite mathematical because it has to do with ratios. Okay, so first of all, you know that intensity, or you should know, intensity is directly proportional and is not equal to, the intensity is directly proportional to area amplitude. Okay, and it's inversely proportional to the radius squared, meaning the further it is, the less the intensity is, and the higher the amplitude is, the higher the intensity is. Okay, now you need a combination of both of them. They need to give you 36 times less intensity. Okay, so how do you know that? Okay, so let's see this. We know that for this particular uh, assignment, we must have that the amplitude that you want, the second amplitude, by the way, this is also squared. I was wondering what is happening there. So it's the amplitude also squared. So we know that the amplitude that you want and the radius that you want, so amplitude 2 and radius 2, they are also squared. They should be 1/36 of the original amplitude. The original amplitude is A1, and the original distances are R1. Sorry, not R2, R1. Okay. So this is the one you want. Okay. And it should be 1/36 of what it is now. Okay. So how do you get this as 1/36 of that? Okay. If, let's check quickly. Okay. If you find the square root on both sides of this, you find that the ratio of the amplitude over just the ratio of that should be, you're finding the square root on both sides, should be just 1/6 times a1 of a2 or r1. Okay, a1 and r1 is what you already have. It's your original distance and your original amplitude. Okay, but you've just found the square root of it. Okay, so now if you were to work it out, you know now, okay, from this ratio, just basic math, you know that a2, your amplitude that you want, your new amplitude, is your original amplitude divided by some unknown number x. Okay, it should be divided by some unknown number x, and your new radius should be your old radius multiplied by some unknown number. Okay, because since this is in the denominator, you need to multiply r, and since a is in the numerator, you need to divide by x. Okay, so this is the situation. Okay, your new amplitude should be the old amplitude divided by some value, and your new radius should be your old radius or distance multiplied by some value. Now they should both be giving you, let me just check here, they should be giving you, if this is what is happening, it should be your old, remember, it should be your old, this is the new radius you want, r a2 and r a2 over r2 should be equal to 1/6 of a1 over r1. Okay, this is your original values, your subscript 1 values, while your amplitude, your amplitude that you want and your new distance that you want should be 1/6 of the old ones. Okay, now you've already determined that a2 is actually just your a1 value divided by some x divided by, and then you've determined that your r2 value is just y times your old r1 value. Okay, and that is 1/6 of this. Okay. Now you can do basic math. Okay, if you were to get that, you will see that x1 x times y times r1 over a1 is equal to 1/6 of a1 over r1 That will cancel. A1 over r1 will cancel with a1 over r1 there, leaving us with the function x times y is equal to 1/6. Okay, so now we're finally at a stage where we can work now. Xy, 1 over x times y is equal to 1 over 6. That means x times y should be 6. Okay, so these factors, whatever factors you're going to change, the product of those two factors should give you 6. Okay, we need these two factors, whatever you're going to change, when you're going to change the amplitude and the distance, when they multiply those values, it should give you 6. Let me just check in the chat. I see Azola, you have a question. Your hand is raised. Okay, maybe another question. Okay, so the factor of the amplitude times the factor of the radius or the distance. Okay, so the radius multiplied by the distance, those two, radius factor multiplied by the distance factor, should give you 6 in order for it to be 36 times less. Let's check now. Okay, which of all of these factors that we've been given gives us a product of 6? Okay, the amplitude factor here is 12 and the distance factor is 3. 12 times 3 is 36, so it doesn't give us 6. The amplitude factor is 4 and the distance factor is 3, so it's 4 times 3, it gives us 12, and it can't be that one. And then the amplitude is 2 and the distance is 3, so it might be that one. Yes, and we can check now. So for now the answer is C. C is a solid option. 3 and 4 for number D, that's going to give us 12, and then 3 and 12 is going to give us 36 again. So if we reduce the amplitude by a factor of 2 and we increase the distance by a factor of 3, will we get, let's now check, A2 over A1 or A2 over R2 is equal to the originals multiplied, it should be 2 times the original amplitude, it is twice the amplitude, and we square that, and remember to square. 3 times the distance, R1, square that as well. Increase the distance, but we decrease, sorry, this should be a half, we reduce the amplitude by a factor of 2, so it should be 2 should be at the bottom there. So basically what we're doing, reducing the amplitude by a factor of 2, is we're halving the amplitude. So we're squaring that. That gives us 1 over 4 over 1 over 9. This is still A1. This is still R1. This gives us, if you take this fraction, sorry, this is not 1 over 9. This is just 9. This is just 9. And then this is A1 still. This is R1. This should gives us 4 times 9, it's 36, 1 over 36. And A1 times R1, which is what we wanted. We wanted it to decrease by a factor of 36. Now, of course, you didn't have to do that whole step that I did. You could have just taken each of those values and plugged it in. Okay, and you would have seen they give out different values. Okay, you didn't have to do it a long way around. I just showed you how you can do it. But if you want to do it by yourself, the easiest way is to just plug each one of those values in. Okay, I showed you the long way. Now I've shown you the shortest way. I've picked number C, and indeed it does work. Let's see if number 1 would work. Okay, let's plug in number 1. Okay, the amplitude, what you want, your new amplitude over your old, your new radius or your new distance. Let's check. If you were to plug in 12, okay, you reduce the amplitude by a factor of 12. So basically you decrease the amplitude by a factor of 12. your original amplitude, over, you increase your distance by a factor of 3. So it's 3. Increase your original distance. You square that as well. Let's see what you get. This is 1 over 44 if I'm not mistaken. 144 times A1. This is 9 times R1. Now, I don't know what 9 times 144 is. Let me check. That is 900 or something, but it's going to be 1 over 1,000 something something times A1 over R1. So it can definitely not be, it cannot be A. So in that way, in that manner, you can check each one of you. You can check A, B, C, D. Which one of them will give you a 36th of the original value? Okay. Now I did, yes. So if you want to do the shortcut way, that is it. But I did do it the long way first, so you can understand how I got to that value. Instead of plugging and checking everyone, I was able to determine straight off the bat, just by determining which one's products will give me a 6. Okay, the product of 6. Okay, so question 21. Which of the following does not have a precise definition in terms of the physical properties of sound? Which one does not have a precise definition? Okay, frequency. Frequency has a precise definition. It's defined as the amount of oscillations that go past a certain point in 1 second. That is just the frequency. It does have a direct or a physical, a precise definition. Intensity also has a precise definition. Loudness is just a word we use to describe the decibel level of a sound. Okay, so loudness does not have a precise definition. Loudness doesn't have a precise definition. Sound level, yes, does have a decisive definition. Wavelength has a decisive definition. So loudness, C, does not have an actual definition. It's just a word we use to describe the decibel level of a sound. Okay, so loudness does not have a precise definition. Okay, loudness never had a precise definition. So question number 2, and we can check. Let's check. Let's say loudness. There we have it. Loudness doesn't have a precise definition. Finally, question 22. Okay, a clarinet behaves like a tube closed at one end. Okay, so a clarinet behaves like a tube closed at one end. Okay, so it's open here and it's closed there. There's the clarinet. Okay, if its length is 1 meter, okay, and the velocity of sound is 344 meters per second, what is its fundamental frequency in hertz? Okay, how do we calculate fundamental frequency? First of all, let's calculate the length of this pipe. Okay, its length, or the wavelength of a wave in here. The wavelength of a wave in a pipe closed at one end is just 4 times its length. So 4 times the length of this pipe, they tell us it's 1 meter. So its wavelength is 4 meters. So it has a wavelength of 4 meters. The sound in there has a wavelength of 4 meters. How can we calculate frequency? Frequency is just speed over wavelength. And the speed of sound is 343 meters per second. The wavelength of the wave in this pipe is 4. So we get that the frequency is 86 hertz. Okay, the frequency in this pipe is 86 hertz. And let's choose 86 hertz in this section, and we find that 86 hertz is indeed the correct answer. The correct answer is 86 hertz. Okay, question number 23. Let me see if there are any questions. None so far. Okay, so question number 23. A harmonic longitudinal wave propagating down a tube filled with compressible gas has the form, okay, that is its displacement, okay, its maximum displacement amplitude, its displacement amplitude. Its velocity can be obtained from, what is a way that we can determine velocity? We know that velocity is equal to wavelength divided by time. Okay. Now, what formula has wavelength in? Okay, it's the wave number. It's k, the wave number. Okay? The wave number k divided by, or rather, let's write it this way. And which one has time in? It is the angular frequency. Okay, so let's say angular frequency. We know from first principles that wavelength divided by time is the speed. Okay, because the time it takes for one wave to go past is that its period. Okay, so that'll be its speed. Now let's say the following. Okay, wavelength is equal to w over k. Okay, if you were to rewrite this, we know that angular frequency is equal to 2 pi f 2 pi f, and wave number is 2 pi divided by lambda. If you were to divide this, you would flip it around. First of all, 2 pi's cancel. Your answer will be then frequency times wavelength, and that is indeed speed. Okay, and that is speed. So angular frequency divided by wave number will give you a speed, and this is what we want. Its velocity can be obtained from its angular frequency divided by its wave lambda. Let's check. So velocity is equal to angular frequency divided by wave number. Okay, and that should be in your textbooks. Okay, I didn't even have to show you the proof of that. Okay, so 24, or rather, is it 23 now? Was that 23? That was question number 23. Question number 24. Just two more after this, and then we're done. So an organ pipe open at both ends has a radius of 4 centimeters and a length of 6 meters. What is the frequency of the third harmonic? Assume the velocity of sound is 344 meters per second. So what is the velocity of sound? So what is the frequency of the third harmonic? How do we calculate the frequency of the third harmonic? We know the frequency of the nth harmonic, where n can be any number, is equal to just n times the velocity divided by 2 times the length of the pipe. Okay, this is for a pipe open at both ends. Okay, these, I don't know if you have done this in PHYV, but for FVV students, you have done this. I have shown you how this formula works. And for the third harmonic, n is equal to 3. So we want the frequency for the third harmonic. F is 3. For F3, it's 3 times the speed of sound. It's 343. Or rather 344. The use in this case. And 2 times the length of the pipe, which is, it has a radius of 4 cm and a length of 6 meters. And if we were to calculate all of that, we find that this is 86 hertz. 86 hertz. Okay, that is the frequency of the third harmonic. And let's check. The frequency of the third harmonic is indeed 86 centimeters. Okay, you just need to know these formulas. Whether you need to, they are in FVV, I give you those formulas, but in PHYV, I don't know where do you get them. But second to last question, the penultimate question. A stretch string is observed to vibrate in 3 equal segments when driven by a 480 Hertz oscillator. What is the fundamental frequency? Now, the fundamental frequency F1 is just equal to f3 divided by 3, because in this case, if it's 3 equal segments, it's the third harmonic, so we just divide whatever frequency they give us, 480 divided by 3, and that should give us the fundamental frequency. 480 divided by 3 is 160 hertz, so the fundamental frequency is 160 hertz. Okay, let's check. Boom, bada bing, it's 160 hertz, the fundamental frequency. Final question, number 26. If a string is stretched and fixed at both ends, okay, 200 centimeters, so its length L is 200 centimeters, okay, so 0.2 meters. If the density of the string is 0.015 grams per centimeter and its tension is 600 newtons, what's the wavelength of the first harmonic? Okay, that is an easy question. If you have done, or if you have seen this formula before, or rather you don't even need the formula, you just need to know that of the first harmonic, the wavelength of the first harmonic is equal to 2 the length. Okay, so it's 2 times, what is the length? The length is 200 centimeters. So 200 centimeters times 2 is 400 centimeters. And that is the correct answer. You can check it. And boom, correct answer, 400 centimeters. And that's all that I'm going to be doing for today. I'm going to release you. If you did not understand anything, please ask me now. Thank you, Alizwa. I try to keep it short. It's Azola. Thank you as well. You guys now can go do something better with your time. Okay, Luluto, can I just ask, which class are you in? If you're doing PHYV, then Dr. David Waswa will be handing you those lectures. If you're doing FVV with me, then those lectures I send out frequently and they're also on the site. Okay, if you're doing PHYV, just get the lecture slides from Dr. David Waswa. Okay. Okay, it has been a pleasure, guys. Enjoy the studies for your tests. Okay, tests and exams are coming up starting next week. All the best. See you guys at a later stage.